Justina is our presenter today. She has been working for, I guess, a while now on photon pileup and Chandra in particular, with the view to extending the same methodology to other things in the future, possibly. See, just tell us about it.
Sure, sounds good. Sorry, did you already start recording? Is that what you did just now? Okay. Right, okay, so thanks everyone for coming today. I know that there are a lot of things going on in outside of science life. So thank you for taking the time. This is work that I've been doing with Vinay and Aneta and Doug, and also Daniela Hoppenhoffen and Raquel. So as background, most people here, I would say, are astronomy experts, but part of the reason that X-ray telescopes are useful is that they enable us to look at faraway objects. Cygnus X1 is not particularly far by astronomical standards, but by human scale standards, it is indeed very far away. And this is an X-ray image created with Chandra data where the scale bar is 1.5 arc minutes. That's about 1/20th of the diameter of the moon. And this is an object that's more than 6,000 light years away. Besides just making images of objects, then taking data with X-ray telescopes also lets us draw conclusions about the properties of the objects. So Cygnus X1 is black hole X-ray binary. And in the illustration over here is an artist's version of what a black hole X-ray binary is, with a black hole and a companion star. And the black hole is accreting material from the companion star into an accretion disk, which is one of the components in this image that it's bright in X-rays. X-ray data is fundamentally formatted as event lists. An event list is a, well, depending on how you order it, it could be a time-ordered series of properties of different registered signals. So the time of arrival of a particular signal, the energy, the position on the detector, quality parameters such as event grade, and so forth. From event lists, then one can produce images like the one I was showing earlier, or you can bin your information in a different way and bin your information as a function of energy in order to get spectra. And X-ray spectra contain information about the physical properties of the astronomical object that you're interested in. In this particular example, the two images here are showing spectra for non-spinning versus for black holes with zero spin and non-zero spin. It's hard to see in the room, but the point here is that the shape of these spectral peaks are different due to the physical effect of if you have a black hole spin, then some of the emission from your accreting black hole will be redshifted, and therefore the shape of your spectral peak will be different.
Just on complete ignorance. When it
Yes.
says spin black hole, what does it mean?
Yes. Okay. So it's a little hard to see in this image over here, but so this is again like an artist's illustration of what's of the properties. So the black hole is a compact object, but it can have a non-zero spin, and it can have a non-zero angular.
It's in literally space, like physical.
Yes.
Okay.
Does anyone else want to correct me on what
I thought
just
there's
said?
nothing in the black hole. So what are these spinning? What are
Well, but we also can't destroy angular momentum. So if the stuff falling in has angular momentum, the black hole acquires that angular momentum.
and it's spinning a constant speed, or is it accelerate, or it's just
So
curious.
I believe that when we think about it, it's constant, but I'm not sure if this is really of its constant on scales that we can model.
Okay.
I should accelerate at some point, but for our purposes, when I talk about spin, I'm talking about one specific value.
Got it. Thank you.
Any other questions for anyone? Including from online. You should I'm trying to look at who has a raised hand, but it's a little difficult for me to see. So just,
Yeah, for the people who are here that have not been to CHASC talks before, feel free to interrupt at any time. We thrive on asking questions as we go along. So, don't worry about making the flow of our decision.
okay. So as I was just saying, then the spectra contains information about the physical properties of the object. But when you make a measurement of a particular spectrum, then you'll have instrumental effects, including pileup. Pileup is an effect that relates to the rate at which you measure frames of your data, and will affect the event list that you infer from an observation, and therefore it will also affect the spectra that you extract from the events list. So knowing pileup well and modeling it well is very important for modeling and inferring physical parameters, such as the spin of a black hole. In the plots over here, so the cartoon at the bottom, or sorry, the plots at the bottom, I had just showed. The top left plot is a plot of a spectrum without pileup in black and with pileup in orange. So once pileup is included, then the spectrum shifts. And at the right is an image of a source with particularly extreme pileup, where actually some of the events get completely rejected. So it's not that there's astrophysically a hole in the center of this image, but that's an artifact of the data, which means that there will be data that's not trusted and therefore not included in the image that's generated. Okay, for what I'm talking about today, I'm going to focus on Chandra and particularly on the ACES-S instrument. So for a little bit of background, Chandra is the Chandra X-ray Observatory that has been taking data for 25 years. Part of the detector includes ACES-S. ACES is an acronym for Advanced CCD Imaging Spectrometer. And here the detectors are CCD detectors, where incoming photons that travel through the body of the telescope and are reflected off of mirrors will eventually come incident on the detector and be converted to a charge cloud of electrons, which will then be translated into the final signal. So the different chips in this detector have different properties. I'm focusing on ACES-S. So in all of the data generation that I talk about, I'm going to be focusing on this particular region in the red box of the detector. Specifically in ACES, then photon pileup happens when your detector registers multiple photons close enough together on the detector within a particular time. So multiple photons can be incident on the detector at the exact same time or shortly after each other in time. But by default, ACES only reads out signal every approximately 3 seconds. And the charge clouds that are produced within a particular 3x3 pixel region are all included in what is inferred to be a single event. So in this cartoon, if you have multiple charge clouds that are overlapping in the pixels of your detector, you may still infer a single event. And the particular pattern of the charge clouds will correspond to the particular grade that the event has. But the key point is, it's because you don't have infinite time resolution that pileup happens. So as I mentioned before, pileup will affect both your events list and your spectrum, because in this particular example that I'm showing, suppose that you have a source that emits photons at 2 particular energies. Then without pileup, you would just observe a version of those 2 spectral peaks. But with pileup, then electrons of these, sorry, not electrons, X-ray photons of these 2 energies can arrive at the detector close enough together in time that you'll get signal at not just the first energy and the second energy, but the sum of the 2 energies, twice the first energy, twice the second energy, and so forth. So your events will incorrectly be associated with higher energies than they would be if you didn't have this detector effect. That's the first bullet. The second bullet point is your event count rate will decrease because if you don't detect every photon and instead detect one event instead of multiple photons, then the event count rate will be lower than it would be ideally. And when events are piled up and come from multiple photons with overlapping charge clouds in the detector, oftentimes the grade can be a grade of worse quality. Grades are typically considered either to be bad or good grades, and it is possible for events that would otherwise have good grades to become events with bad grades once they are piled up. So here's an example with a slightly more realistic looking spectrum, just to illustrate the point that if your idealized source spectrum was just a power law of your intensity of let me say it in the units I have. Your log intensity being linearly related to your log energy, then without pileup, you would get this green spectrum, which has a particular shape and a particular slope at various energies. But with pileup, then you get a different spectrum from which you would infer a different slope. So really understanding pileup is important for taking measurements from the spectrum that relate to physical parameters. Any interruptions before I move on?
Yes, actually, I guess now is a good time. Pileup is sort of inherently a time domain effect, and so I would have thought naively the most dramatic effects would be in light curves. But I mean, you mentioned that it affects the count rate, but you've emphasized the spectral, all the spectrum, the influence on the spectrum. Is that just a choice of convenience, or are the methods that you're going to talk about focused on energy spectra, not time domain things, like looking for rapid transient effects in variable light curves?
Yeah, I haven't thought about applying this to light curves just yet. What I'm talking about today is really focused on energy spectra, So I think that there's some version of this that would work for light curves. But maybe as I go, then there may be some parts where it will be very clear that you would have to treat the data a little bit differently when it's a light curve instead of a spectrum.
Okay, thanks.
Sure.
Can I make a quick comment
Yeah.
on that? I think having a spectrum makes it easier to figure out what the magnitude of the pileup effect is. So if you just see a spectrum and you got a count rate that goes to 0.9 counts per second or 1.2 counts per second, you can't just invert it without knowing what the spectrum is doing.
Sorry, could you repeat that? I'm not sure I followed.
I'm saying that the spectrum gives you a handle on figuring out what the magnitude of the pileup is.
Yes.
Which is hard to do with just the light curve.
Yeah, that is true. When you only have the light curve. Yeah.
If you have the light curve and you knew the spectrum of the object,
Yeah, you would.
that
Also
would be okay.
It's not, I mean, not just the spectrum, but also the grade distribution and how the grades are changed.
Yeah.
All that lets you figure out how much pileup there is happening.
On the light curve, we also often do agent because you can draw light curve from the pileup, from the readout street, or from the extreme corners from the outside of the PSF. Because if the object is that bright, you have enough signal anyway. But for spectrum, you want to use all of it because you have a lot more spectral bins you need to worry about. So what it says true in practice for light curves in Chandra, it doesn't matter that much because there's other things we can do to get clean light curves.
That's a very good point.
What's that? Yeah.
I would also argue that you can't actually solve the light curve problem without solving the spectral problem first. Because clearly the flux that you get as a function of energy will depend upon your pileup. And so any variations of the flux of the source will change with energy, and you got to figure out the energy problem first.
Well, if I could offer a alternative, Herman, that's a great point. But the way I think of it, maybe this is unfair, but in the time domain, it's a first order effect. In the spectral domain, it's sort of a differential effect that different energies are respond to develop pileup in different ways. So it's kind of like a second order effect, and that's why I made the comment that I thought time domain effects would be more dramatic than spectral effects.
It's not even monotonic in time, though. With flux, as you increase the flux, you'll get a point where it turns over and it can be double valued, and there's a given count rate will actually be appropriate for two different input count rates. So you can't really solve it very easily by just looking at the count rate.
Sure. Well, I don't want to belabor this, but could we talk in the context of a source where the spectrum is not varying with time, that the spectrum is constant, and you're just interested in varying in estimating the average spectrum or the light curve in the other case? Would you agree that that in that context that you really don't need to solve the spectral problem before you can deal with pileup in the light curve? Or maybe I'm wrong about that, but I think in that case you can sort of ignore it because it's not changing. The spectrum isn't changing.
If you've got pileup and you then the spectrum will change. So
Well,
if you're gonna have a light curve where the flux changes so much that the pileup is an effect somewhere in there, the spectrum will change, and you can't then just assume that the spectrum was constant.
do you mean the estimated spectrum, or I'm thinking of the true spectrum? Let's say the spectrum is constant over time. That's what
How can you tell? How do you know?
Oh, well, I'm just assuming that for the discussion. I don't know. This is getting.
It seems easier to assume time independent source flux and a known spectrum or a model spectrum that you can then try to figure out what the pileup is for that, and that's the problem they're solving here.
Can I make a quick comment, Jeff? I don't know if this is the problem that you're thinking of, but sometimes, when you have a flare, the count rate goes up a lot and there's going to be a pileup and the spectrum is going to change. But the spectrum is going to change regardless because there's been a flare. So there is going to be some sort of compounding effect where, for example, you're going to get a harder spectrum through two effects. And the only way to figure out exactly what's going to happen, what happens at any given time, is to do the problem in all the dimensions of it.
Sure, absolutely right. But both they're intertwined. You can't separate time and energy, the energy domain from each other. Absolutely, but I just think in terms of most of my work is looking at light curves for fast variability, and I don't care that much about the spectrum. So I have a kind of a bias. I would have thought that the best way to attack pileup is modeling it in the time domain, and maybe that's what you're going to do. So maybe we should move along, because maybe what you're about to talk about will be important. So.
Okay, yeah, if you have thoughts at the end about how to change what I'm doing from energy space to time domain, then yeah, we can definitely talk about that again.
Thanks.
Okay, So to move on a little bit and still give background, pileup is only one part of the instrument response. So part of the response is described by the ARF, and part it's described by the RMF, both of which are fairly well understood in the sense that they're calibrated, and when they change over time, then the calibration teams update what the ARF and RMF are inferred to be. So the ARF sets the overall shape of the spectrum in the sense of the ARF parameterizes the effective area of the telescope and other similar properties, whereas the RMF broadens the signal. So in this particular example that I was showing with simulated data, where the incident spectrum simply has 2 lines, then the simulated observation that has no pileup still has some signal broadening of those 2 peaks, which comes from the RMF. The RMF just maps the incoming photon energy to the output channel with some broadening in it. And I guess related to what we were discussing earlier, pileup is a photon level event in the sense of if you know all the properties of the incoming photons as a function of time, then there is a physical process going forward which exactly describes what the output, what the pileup output is. But it's very difficult to model this from first principles. So currently the standard is to use the pileup model from Davis 2001, which the key point about this model is that it has a parameter alpha that parameterizes the probability of grade migration. To be precise, alpha is the probability that the combination of a collection of photons has a good grade, assuming that the collection of photons minus 1 had created an event that had a good grade. This value can be a value between 0 and 1. Oftentimes it's 0.5, although you can make choices for alpha when you do parameter fitting. And this model works more poorly for sphere pileup. So if you have more than 10 photons that are incident on the detector and that produce a pileup event, then this model doesn't work so well. But it is a standard model, it's implemented in MARCS. And I'm going to be talking about it a lot because it's going to come up in my model of training a neural network to try to match a simulated version of pileup. So just to talk a little bit more about MARCS, I will use it to simulate training data. MARCS is a Monte Carlo simulation of tundra observations. It is really the best available simulator to create mock tundra observations, but there are some other codes available which one could use to generate similar mock pileup observations. Which one? 60. So 60, yeah, SIXT.
Yeah. That's a very important ones.
So 60 is different than Mach, in the sense that Mach is a range range code. Which has a physical understanding of where like detectors and stuff are in space. And 60, on the other hand, has much better detector model than Mach has. So 60 knows about the depletion depths of the CCD, so the actual thickness of the layers of silicon. And so it's different. Or their strengths are different.
So to move on, what I'm going to be talking about today is whether a neural network can mimic a simulated version of pileup. That's the Davis 2001 model. And then eventually I'll talk about how, with additional work, we anticipate that you could extend this to mimic the empirical version of pileup that happens on the detector. So why use a neural network? It's a useful tool. Neural networks are good function approximators, and we're interested in using a neural network to directly distort the spectrum that is idealized and contains no pileup into the spectrum that does include pileup. Part of the reason, another reason that we're interested in using a neural network is that this is much faster than producing pilot observations through other means. So MARCS can produce pilot observations. It can therefore produce mock pilot spectra, but that will take much longer than evaluating a neural network once a neural network has been trained. And for comparison, not including the training time, then with the trained neural network, it runs in about 1/100th of the time that a MARC simulation to produce a similar spectrum would run. Okay, so conceptually, here's the neural network model. Starting from various physical parameters and a known spectral model, then one can produce an incident spectrum. And combining that with detector properties, namely the ARF and RMF, then you can get an incident spectrum with the instrumental response. And the goal is to have a neural network which will map that to a pilot spectrum. The goal is to have a neural network which will map that incident spectrum, including the instrumental response, but no pilot, into the pilot spectrum. And the particular case of parameters and spectra that I'm going to talk about is, again, thinking of the case of a black hole with an accretion disk. So the various parameters, which I'll show later on, are the power law index of radiation surrounding the accreting black hole, the inclination of the black hole relative to the accretion disk, the column density of hydrogen along the line of sight to the source, the ionization of the accretion disk, and the spin of the black hole. And then the particular spectral model that I'm using is Rauxel. But this model is fairly generic. We believe that for other astrophysical sources, then you could substitute in group parameters and spectral model that you want to use. And the goal here is to eventually use this to infer different parameters. Starting from the parameters and with a known spectral model, running the trained neural network to get piled up spectra, which then can be compared to an observed spectrum to infer best fit parameters. Ultimately, that's the goal. So here are some details of the neural network. First of all, this is trained on training data that's produced with MARCS. The training data is pairs of incident spectra that include instrumental response, but no pilot, and spectra that are simulated with MARCS that include pilot and also that include Photon noise. So that's the point from this gray box. The neural network itself is pretty simple. It's a fully connected neural network with 3 hidden layers, each of which has 256 neurons, and each of which has a ReLU activation function as going into the next layer. We also trained this with dropout, but really no other modifications to this neural network. So it's a pretty simple model, relatively speaking. The input to the neural network is, again, this spectrum that includes the instrumental response, but no pilot. So, for example, in this spectrum that I've put up here, the overall shape with these 3 slight peaks in it comes from the shape of the ARF. The training data, which the neural network treats as the target that it attempts to match, is the simulated spectrum from MARCS. And the neural network prediction will be a spectrum in units of counts per second, but transformed in such a way that it's easier for the neural network to deal with. And optimization for training this neural network is done by minimizing a mean squared error loss between a transformed version of this training data and the neural network prediction.
How much pilot do you have in your training? It's probably range, but is it like mostly little or mostly a lot? Or?
Yeah, it is a range. It's mostly a lot right now. There are some with small amounts of pilot, but most of the time, the difference in amplitude at a particular energy of the non-pilot and pilot up spectra is going to be at least a factor of 5, oftentimes more than a factor of So yeah, mostly severe pilot. Any other questions?
Which does strike me as kind of extreme, but I guess you are just in this flare case, right, where you do the observation and the thing was 2 orders of magnitude brighter than you expected. I just feel like in general, if something is so vastly bright, you're doing something wrong.
For the specific case of black holes, I'm not entirely sure what Daniel and what you guys are after.
Yeah,
Yeah,
But in general, I think we see a lot of instances where there's so much pilot that the source basically wipes out.
Yeah.
I don't think we are dealing with that severe pilot. So even though it seems large, it's still not as large as it.
okay.
Sure, but if the source is entirely wiped out and there's no signal, then there's nothing left, then
Yeah.
there's nothing
Yeah.
you can model, right?
But no, but you can get the thing.
Yeah, but then,
But, and I mean, even if it's a factor of 5 or 10, that's kind of saying there's 5 or 10, 5 or 10 photons per pixel in the readout, right? Yeah, at least in this 3x3 pixel region or something.
Right.
And that's so many photons, I feel like you have no chance of recovering what actually happened. If there's 2 photons, sure, or 3, but by the time you get up to 10 photons, like, no algorithm can tell you what happened.
the detected photons, though, that I'm actually making your spectrum will typically have less than 10, because if there's 10, then such a small chunky area, the grade is gonna be so bad, or the energy is gonna be so
Yeah.
high, that's we rejected on board.
I see, so
So
the
you won't actually
surviving
have that.
photons.
The photons that you actually make that, but the grades are good enough that actually makes it to the ground, will typically have no more than 2 or 3 or so photons in it.
Oh, okay, good, I find that very reassuring, actually.
I still think it's an interesting choice to start in the area where the pilot model probably doesn't work that well.
sure.
Whereas like
Yeah, I
in a
take your point.
fairly moderate pilot case, I think that's what the model has been developed for, and where we can compare observations and know it works reasonably well. Whereas this is I think for the model, this is already a pretty extreme case where I'm not John Davis, right? I'm just responsible for Marx today.
Yes.
But I wouldn't bet that it works. In fact, I would bet that it doesn't work in
Yeah.
some way.
Right.
Yeah.
But the thing is that she's only using, right now, everything is built on the simulation.
Right. But if so it's going to you recover it from simulations. But if the model if your simulation isn't good enough, then you won't ever be able to transfer it back to use it as an observation.
Sure.
Yeah.
That's problem too.
Yeah.
Yeah.
The quick question about this, so
Yes.
the Marx spectrum that you get, they are built only from good grades?
Sorry, they're built on what?
The Marx spectrum that you get?
Yeah.
They're built from good grades only.
They should be built from good grades only. I
Grades
will,
Marx assigns to photons are fantasy.
that is also true, yeah.
They're not, they make files that have the correct fixed pitch file structure. But the way the grades are assigned is not full fantasy, but it's like Disney movie fantasy. Okay, there's princesses, there's kings, and those things exist in reality, but beyond that, it's not real.
If I remember correctly, there's a table somewhere with probabilities of assigning different
Yeah.
grades to different events, and it's self-consistent, but it's
It's
a
not
approximation,
like
right.
it's a grade 0 event, which means you only detect it in one photon, and then you only detect it in the center of the pixel.
Right.
If you run a Marx thing and your photon hits the center of the pixel, you're gonna get a grade 0. But in a true observation, you'll also sometimes get other grades, and Marx just won't give you them. Right, Marx will also only give you, I think the list has like only 12 or 15 grades in it, but the real observation will have 100 grades.
Yes, I will make a note of things that I want to follow up on.
Yeah, no, that's helpful information. I was gonna ask about the ReLU again, we talked about this weeks ago, and then other things were higher priority. But my understanding is, in a simple feedforward network like this, if all of the activations are ReLU, you can only ever get piecewise linear functions. Right, and it seems like you want something smooth here. If you
Yeah.
even put a sigmoid type thing in anywhere, in any layer, even once, then that's not true anymore. But if everything everywhere is a ReLU, I think your result is always piecewise linear, which might be kind of weird. Like, for example, if you put in some, reference spectrum and you slowly move it up and you plot the mean of what's being output, I'll bet it's, it might have many, many pieces, but I'll bet it's piecewise linear. So
Yeah,
it's
I
just
think-
something to think about.
Yeah, this is something that I haven't revisited since we talked about it. It is the case that the actual input and output that the neural network is trained on aren't linear transformations of the actual spectrum, because there's a log in there.
Mhm.
So if it's piecewise linear in the transformed version of the spectrum, then one should still be able to get smooth output spectra. But I guess this is,
Easy to try out.
yeah, fundamentally it's still piecewise linear. So
Yeah.
this is something that we can try.
Well, like I said, the limit was a huge number of pieces, it doesn't matter.
Yeah.
But your neural net's actually pretty small and simple without a lot of layers, so it
Yes.
might be something to wonder.
Okay, any other
Uh,
comments? Yeah.
So just to follow up on that, so I think the number that we chose here, supposed to match the number of channels that were available. So 256 times 3 match 500 or 600 spectral channels, so wasn't that the reason?
That was not, that may have been subconsciously a reason, but that wasn't something that I was planning on. It was just that originally with extremely narrow layers with say 10 neurons, it wasn't working so well. So we scaled up by a factor of approximately 10 and then went to a nice power of 2. I didn't intend for the number of
There was one.
individual neurons to be similar to the number of channels.
But
Yeah.
does it matter that it is or is not? Suppose you went to 1024.
Yeah.
And 15 layers. Would it make an improvement, or would it have already asymptotic to the solution?
There's only 17,000 pieces of training data.
Yeah.
You probably have too many neurons in your model,
You can always make
but you'll need to make a lot bigger training data. And then the question is that if you train this on more training data, it will also be better.
Well, there's a lot of regularization in there. I've always been disturbed by the fact that people can train models with far more parameters than the data they're training with, and it doesn't, you would think that would completely blow up. But they're also regularized in various ways, so I don't, it's not obvious. You just have to try it. But yeah, certainly if the number of neurons is way too small,
Yeah.
which I think it originally was, then you're very
Right.
limited, that's for sure.
Right.
And your last layer has to, one side of the matrix has to have the number of channels as. Because you're outputting,
That's what I remember. Yeah, that's what we were aiming for, right?
Right, well, so this is, there about 600 channels in the input and the output. So the dimensions are 600, 256, 256, 256, and then back.
I see.
So I'm not sure if that answers what you seem to have been thinking about, whether 256 is the right scale.
I mean, it's probably fine, it's sort of saying there can be at most 256 degrees of freedom in the spectrum, and it seems generous.
Yeah, I did.
So.
Yeah. All right, so let me show some results. This is a particular draw, but generally the neural network does fairly well at reproducing the Mark simulated pilot spectra. I only have 2 representative examples in this particular presentation, but we can discuss more where this might break down. Generally, though, it does reproduce the pilot spectrum that Marx predicts fairly well. So in this plot, the inset plot is the incident spectrum in physical units, which doesn't include any RF or RMF from the telescope yet. The green line is the incident spectrum with the response. And for reference, this dashed line is an approximate scale above which we would expect to have happening. The blue is the neural network prediction. Sorry, the blue is the Marx simulation and the black is the neural network prediction, where the goal is for the neural network prediction to be the mean spectrum that you would get if you took multiple mark simulations repeatedly, and therefore could average out the Photon noise. So here the neural network prediction does seem to be consistent with what the mean of the mark simulation would be. Incidentally, this is also run for, the mark simulation is run for 50 kiloseconds, which is a reasonable exposure time, but slightly on the longer side. And at higher energies, then that spectrum is running into fairly low counts. So it's difficult for the neural network to constrain the prediction at those higher energies. There's another example with a slightly lower amplitude and a slightly different shape. This is an example that has more absorption, so the spectrum is overall lower at lower energies. And again, given the caveat that at low energies, there are not too many counts for the neural network to work with, the block neural network prediction seems to do fairly well compared to the mark simulation. Any questions before I move on?
I'm just a little confused. Are these plots, they're labeled as piled up spectra, but are they spectra corrected for the pile up effect, or are they simulating the pile up effect?
The blue line is simulating the pile up effect. So everything that I'm doing is going in the forward direction, where I'm starting from the distant, where I'm starting from the.
You're testing how well the simulations work, but and then now you're about to tell us how to correct for pile up. Is that what follows?
Unfortunately not. So I don't have a way. I am currently not working on a way that will undo pile up. What I'm working on is a faster way to evaluate how pile up distorts the spectrum, so that you can do forward modeling faster and then deduce parameters that produce best fit piled up spectra when compared to observations.
Okay, okay, thanks. And one,
If I may rephrase, I think what Justina is doing is effectively building a black box model. Instead of a tabulated model, she's got a numerical model that goes from parameters to observation, and she's working on figuring out what the parameters are. I don't know if you're going to talk about any fitting procedures, Justina?
Yeah, a little bit.
So yeah, imagine doing an MCMC fit from like where you start from your also parameters and then predicting the actual spectrum and then figuring out what the likelihood is of the match and then estimating the best fit values and the uncertainty on the parameters that way. So that's as opposed to deconvolving, right? That's
right.
That's it.
okay, I understand, and maybe this question is really irrelevant, but does their model of pileup distinguish between photons that arrive at exactly the same time from those which arrive just close together within some threshold of delta T?
For what I'm doing, then there's no difference.
And sorry, is that because you don't explicitly make a model for the arrival of the photons? It's sort of pushed off into the neural network to do that for you? Is that the reason?
You're using Spectra, right?
Yes.
And the Spectra are based on event lists, and the event lists don't have that information because we only read out every 3.2 seconds.
Right. Right. So it's sort of, well, okay. So that's what I'm getting at is and it's not a criticism, but I'm just trying to understand, you're not explicitly modeling the nature of how the detector responds to photons close together in time. You're just learning, you're using supervised learning to to model that for you implicitly rather than explicitly. Is that a fair statement?
Yeah, I think that's right. It's definitely true that what we're doing does not work on building a model of how the detector responds to the photons. And it is definitely true that the in the model that I'm using, I'm collecting all of the photons that are measured within the 50 kiloseconds and looking at those all together. So the other point that I was going to say was, sorry, you said something about doing this implicitly. Well, okay, Vinay, you can go ahead, and I'll remember what I was about to say.
So, no,
One other quick maybe footnote. The reason I asked this is that it's sort of a crazy idea, but there's sort of a renaissance in coherent effects, Hanbury-Brown twists, interferometry, and so on. And photons are bosons that can bunch. So in principle, if one is searching for coherent effects or photon bunches, it sort of mimics, in a sense, two photons bunched together get recorded as a single photon with twice the energy, and things like that. But the discrimination between that and between bunching inherently in the source and pileup might be in terms of delta t, that the inherent bunches have 0 time delay, whereas the pileup presumably has some finite detector-based time delay. And so I would think an interesting approach would be to make explicit models of pileup from a detector point of view, and maybe you could make some progress in detecting these exotic coherent effects. But it's just a crazy idea. I don't think it's ever been realized in high energy at all, that people are doing it in optical and infrared, but not X-ray.
I think if you wanted to do that, you would look for a source that doesn't have that the count rate is low enough that you don't have to worry that much about the detector. Or it's also your readout faster, like in fast window mode or in CC mode for Chandra, or in like the burst mode for XMM or something like that. So you don't have that effect on top of what the one you're looking for, which looks exactly the same.
Yeah.
But it's on top of what you are looking for in a way that you don't fully understand. So I don't think this is the right data to look for that.
yeah, and I what I wanted to mention was we're making this assumption of, underneath all this, that the detectors are still responding linearly. So even if you have 10 photons coming in, the charge cloud that they produce is equivalent to 10 individual photons. It's just that they get superposed and we can't tell in the readout. But with the new methods like Athena or anything with calorimeters, what Jeff suggested could be visible. I mean, we got heat pulses from the calorimeter that pile up so closely that it would have a different. It would. I think that the detector would respond differently to things that are bunched more compared to those that are bunched. But maybe, yeah, we'll have to think.
But then wouldn't you still have, sorry, that's, in that case, I think that you would probably still have to do it more with saying of using some observation that doesn't have very much so that you can separate those two. But I don't know, it could be that that's less
It's going to
important.
be hard to find cases where you just have intrinsic photon bunching versus no pileup, or maybe with very, very fast readout.
Very fast readout, gratings that split it over like about the detector area.
Could I have one other, I think maybe even crazier idea, but I don't know if you're familiar with the NuSTAR approach to pileup. NuSTAR has 2 independent focal plane arrays, and so by doing, for example, in estimating a power spectrum, they can calculate a cross spectrum between the 2 the data streams from two independent focal plane setups, and that apparently, and they developed a method to reduce or eliminate pileup. Is there any way of mimicking that in Chandra? Is there any way of getting, by selecting, I don't know, from the positional data for a point source, that photons that are independent and can be analyzed separately?
We've got Christine on the line. I don't know if he wants to comment on this. I'm not familiar enough with.
I mean, you kind of do that when you take a spectrum of the readout screen, for example. Right, we would use about unpiled up parts of the detector that contain the source spectrum. And so Chandra, that's the readout stream. Or is, if your source is bright, that's like the outer ring of the PSF. You would extract the center, which is piled up, and then a ring around it, which is much less or no piled up, depending on how far away from the center you go.
And
And so you can compare those.
And in at least one case, we've used the dispersed events as a way to work around the zeroth order pileup in trading data.
So for what you were describing with NewStar with the two focal planes, would it be possible to do something similar by saying from a list of events that are distributed across the PSF, take within a particular ring a random selection of those events, and then count those as one spectrum, take the remaining points, count those as another spectrum, and then compare those and see whether some parts of it have pileup?
Well, the answer to that is, I mean, someone who knows the details, I think that depends on how the data system and detector works. And I don't know the answer, but I'm sure people sitting next to you do. I mean, are those photons really independent, or are they, is there some dead time? For example, dead time is a related thing. Is there a dead time influence that does a photon in the middle of the PSF cause a dead time for photons anywhere in the PSF? I assume so,
No.
but
I think so.
No.
No.
More no.
Herman has a comment, I think.
Yeah, I wanted to change the subject actually. But there's plenty to talk about there, and I think there's something more to be said there. But one of the things I would like to have seen on this figure, maybe it's coming up in the validation, is the version that the neural network predicted was the before spectrum, before pileup. In other words, the green line against what it was, against what the neural network says was the before spectrum. Is that coming up?
No, that's not coming up because I don't have the neural network predict that.
No, the green is yours.
So
The green is the input to the neural network.
yeah, let me go back to this chart because I'm not quite sure which part in here you're looking for. So the green is the spectrum that doesn't have any pileup. It's includes the ARF and RMF, so it's a count spectrum. But that gets passed to the neural network, and the neural network predicts a spectrum that does include pileup. So you were just saying that you would have liked to see what the neural network predicted that didn't include pileup. Is that correct, or am I not understanding?
Yeah, I guess I just don't see a feedback loop here essentially that says you can estimate what the original spectrum was via the neural network, because the neural network figured something out, right? It figured out something about the input that led to the output. And therefore there's something
Right.
in there's some result in there, or some inference that says, here's what was the input spectrum was that gave you this piled of spectrum.
I see. Okay, so I don't have.
I don't think it's trained that way. It's trained on the, it's just a faster way to apply pileup. It doesn't unapply pileup, because then you'd have to train it the other way around.
That's right. So
Yep.
the neural network only applies pileup. I don't have something that would show I don't have a plot that would show something similar to what you were describing, but I do see a way that I could do that. Where in the inference process, where I said some parameters produce neural network predicted spectra that look like the observation. What non-piled up spectra would those same parameters give? And how does that compare to the green line I was plotting? But that's a extra step beyond what I'm going to talk about.
Yeah, okay.
Yes.
Just to clarify, the blue line is if you run the marks simulation once and get it, if you run it multiple times, I guess you get different.
Yeah, like you're asking, if I were to
Yeah.
run marks multiple times, I would get different realizations of this solution.
And you're saying like the black.
So that's a check that I haven't done in detail yet. Right now, then this is just a comparison of this black line seems consistent with the mean. Seems consistent with the mean spectrum that you would predict, knowing how much noise there is in the spectrum. So I don't have a plot that will show the overlay of the different marks realizations compared with neural network. Yes.
I guess I can imagine it.
Yeah, so John was saying that with dropout on during evaluation, then we could get different realizations of neural network.
Yeah, because I guess, I don't know much about the mark simulation, but do people typically use the mean and the bunch of them, or like individual ones? Because there's still like between the.
Yeah. No, I actually don't know. I don't know when people use marks for analysis, if they take many marks simulations and then average them, or if they have a preferred way to do it.
People use it for different purposes.
Okay.
Mainly to make calibration data originally. They would just run it over 100 million photons or something, and then you don't have to worry about that. That's the same thing as running it 100 times over a million photons.
Yeah.
Because in Monte Carlo code, and assuming the code works and you don't start from the same seed every time, it doesn't matter how you get your number of photons.
Oh,
No, I was just gonna say, going off of that, I don't know if we already discussed this, but we talked about like different realization. But like, have you thought about the different?
okay, so the question is, have I thought about fitting an uncertainty to the spectrum?
Uncertainty at what stage?
Well, I mean, like, instead of just allocating one spectrum, you could also like.
It's a song realization, so we know what that's. Yeah, it's like every bit is a song realization, so you don't have to fight, you know.
Yeah, okay, yeah, go ahead.
Does the power typically depend on the spectrum? Yes. But we don't put those into the neural. Maybe. Those.
They implicit in the green bit.
Okay.
So going back to this slide, the spectral model, right, so the spectral model does influence how much power you get.
Right.
Could you say,
Not if you want to use this on real observations to drive the trend.
Oh, I see. That's spectrum as being like an emulator, like. Yeah, not.
well, I don't quite understand what you were saying to impose in the neural network.
Oh, just you basically use them as input to the.
Or instead.
Oh,
and you
okay,
could
I see,
train the
sure.
neural to go from the parameters to the spectrum. So the full simulated spectrum, as opposed to just going from the spectrum, you could do that.
Right. Here we decided not to do that because Roxo already exists. So we have So there is already a method to get from the parameters to the instance spectrum, which then can go into the last version of the spectrum that doesn't include pileup, which is what I want to give to the neural network as input.
And the other thing is, if your spectrum, I mean, this is all fine, then it's a simulation, but in reality, your spectrum might specify your spectrum. In which case, you don't want to be limited to just that one particular model. So you might want to set a power law, and then the parameters change. Good to have that test.
There's another very good reason to do this way, which is the ARF has changed considerably over the course of the mission. Right, so you kind of like to train one neural net and have it work for any ARF. Otherwise, you have to train a neural net for every ARF or make it explicitly dependent. Like it makes the problem much more complicated. So yes, you could do it, but we're trying to get the simplest thing to work there.
It doesn't mean it might be useful to train it with green spectra that are made with different ARF and with different models. Because the dependence from the shape to the piled up will depend on what the ARF is.
Yeah.
So if you train it on one particular ARF, it's only.
You can only count on it to work on that ARF. Yeah.
It's optimized to work for that particular ARF
That's a good point.
and for that particular spectrum.
Right. Yeah, one thing I didn't mention is that in these 17,000 sets of training data, those are all done with mark simulations that have the same exposure time, same ARF and same RMF. They're all for point sources that are on axis. So there are a lot of other parameters that we could vary. So yes, with different ARFs, then we would have a lot more training data, which would show the neural network piled up spectra from different stages in the mission when the ARF looked different.
I don't think you have to worry. If you change the normalization of the model or the flux of the model, you don't have to worry about the exposure time because those two are redundant, right? And the data, the data only has a number of photons per bit, and that's like the intrinsic normalization and the exposure time are somewhat redundant, not exactly the same.
I think the normalization controls conflict.
Yeah, I guess that control.
Depends on count rate, yeah. So we do have to be careful.
Yeah.
Yeah, that's true. Everything that I'm doing here is with spectra that are in units of counts per second. Okay, so let me show some preliminary work using this in an MCMC, where the MCMC is attempting to optimize a log probability that is the product over all channels of observing the blue marks spectrum in that channel, assuming that the mean of the Photon distribution is what's predicted by the neural network in black. So sorry, I didn't color code these. The point here is that this is fundamentally a Photon probability. And even though I just said I'm dealing with counts per second spectra, in the evaluation of the likelihood that goes into the MCMC, that I'm working in counts, so that the probability is based on how many counts do you see over your 50 kilosecond exposure, assuming that the mean is what the neural network predicts. So preliminarily speaking, then the inferred parameters from the MCMC correspond to piled up spectra predicted by the neural network that are roughly consistent with the mark simulation. So in this spectrum, the blue is the mark simulation. Again, this includes Photon noise. The gray lines are different draws, are different predictions from the neural network that correspond to draws from parameter space of the original 5 parameters that went into the physical model. So like I said, the spectra that the neural network ends up predicting are roughly consistent with the mark simulation. They do correspond to different parameters. They do have different amplitudes at around 4 kV and below 1 kV. So there's a trade-off in the optimization here, which is causing the MCMC to pick out different regions in parameter space as the best fit parameters. And here's another example for a different spectrum. This is similar to the other spectrum that I plotted, which had a higher amount of absorption, meaning that there's more hydrogen along the line of sight, and the spectrum at lower energies has relatively fewer counts. So let's see. It's rather difficult to see on this slide, but most of the draws from this particular MCMC end up producing spectra that lie close to what you would assume by eye. It's the mean of this Mark simulation. There's a very faint one over here that you kind of can't see, but that's from a different region in parameter space. Okay, so after this, I have a few more slides. Those are talking about how this neural network could be adapted to actual Chandra observations. But this is the end of what I have that's validating the neural network to emulate the simulated version of pileup, the John Davis model of pileup that Mark's influence. So let me stop here and see if there are questions.
See any questions?
Only a representation question. So these blue spectra that are they're discretized in counts. You nicely put the 1 count mark on the right there. But there's a lot of bins up towards 10 kV, and so the blue lines are kind of low. I could imagine that black line is going through the mean of the blue nicely, but I have no idea actually. Would it be possible to bin or smooth the blue in some way? I mean, I don't know. Vinay has seen a lot of X-ray spectra. What do people do when they've got hundreds of bins there, channels?
People do what they call it, they group the spectrum, so they're at least minimum number of parts. So they trade off resolution with smoothness, I guess. So
yeah, I'm not quite sure what to want here, but I just think it could be represented in a way that makes it more clear that the black is going through the blue nicely. Or if it's not, we need to know that.
Yeah. And also, like, this type of plot is really not really the right way to be doing science. Of course, the better way to do this would be to report various goodness of fit metrics. So that's something that I'll continue doing.
One specific thing about Chandra spectra is that when people do these fits, they usually do the fit between 0.5 and 8 kV at most. So the fact that you are doing fit for extended range.
Yeah, you put it at 0.4 and maybe between 0.5
Yeah.
or 0.6, like that's not very good down there.
Yeah, the ARC is not, the RMF is not well written.
Okay.
And beyond 8 kV, that's usually not enough counts.
Right.
Okay.
Yeah, for all of these, I'm going from 0.4 to 10 kV. So that's broader than the standard range.
Something to keep.
Although for the present tests, the neural
Yeah,
net mimics marks or it doesn't.
Yeah.
This has nothing to do with Chandra.
So,
But yeah, it will.
Okay, so moving on, let me describe how this neural network could be adapted to mimic the actual version of pileup. The main point here is that observations that are taken with the higher energy transmission grading will disperse photons across more pixels, and therefore in these dispersed spectra, there will be less pileup. So for particular observations, pileup there will be low enough that it can be assumed to be effectively 0. And then those spectra from those observations can be used as unpiled, quote unquote, ground truth spectra. Which after some processing, knowing that we have to adapt the HETG observations to say have the same RF and RMF as the type of spectra that I was showing earlier, then we should be able to build a training data set of unpiled dispersed spectra and then also piled up spectra, which are just would just be obtained from the 0th order image of the source. And looking at the available data, I predict that there are about 1,000 pairs of training data that you would be able to use, which is not much compared to the 17,000 that I was training this neural network on for a pretty restricted version of pileup. So I think we have yet to see if this can actually be used in order to train the neural network on first simulated marks data, and then on these about 1,000 sets of actual observed data. But it's certainly worth a try. And we expect that with enough training data from mark simulations, then the neural network would get to a point where it mimics a version of pileup that's close enough to the actual version in Chandra, that continuing to train on these 1,000 data points would bring it closer to the real version of pileup. And then the last point that I have is related to what Vinay was talking about with a different detector technology, where in transition edge sensor microcalorimeters, the version of pileup that happens has more to do with different pulses of the signal overlapping in time, and then being associated with better or worse quality events. So this is similar to the version of pileup that I've been talking about, but it's different because the energies of these signals don't add up. But all the same, I don't remember the name right now of the simulator, but there's a simulator for Athena observations, which ought to be able to be very similar enough to marks that if people were interested, they could do the analogy of what I've done with marks and a model of Chandra pileup for this type of detector on Athena to mimic how that version of pileup can be approximated by a neural network. Okay, so conclusions from what I've talked about today are that the fully connected neural network that I showed a few slides ago can emulate the version of pileup that shows up in marks, which is based on the Davis 2001 model. I showed a few draws from the MCMC to show that pileup spectra corresponding to draws from parameter space reasonably well match the simulated data from marks, but still there's more work to do there. And then future work will involve transfer learning with the actual Chandra observations taken with the HETG that disperse photons into the grading observations and therefore have less pileup. So we have a few more minutes. We should, of course, discuss the questions that came up, but also if you think that you have a version of pileup, possibly not in Spectra, possibly in time domain, let's talk about that too.
All right. Any questions from the people online? Comments? Yeah.
Well, I seem to specialize in crazy ideas, but sometimes neural networks are said to actually learn in a creative sense. I think it's rare, but sometimes a neural network can solve problems that, in some sense, were not part of the training data. The one case I know about has to do with modeling of strong gravitational lens systems. But I guess my question is that anything that you've run across in your simulations? I'm not even sure how you would see that. And what you're doing, you're not solving an inverse problem like they did in the lensing situation. You're sort of solving a direct problem, and I'm not sure how you would find anything outside the scope of the training data, if that makes any sense at all. Is that a completely crazy question?
I think that's a fair question. I don't think that we've found anything in our results that is especially surprising. I think the neural network is just using either a piecewise linear approximation or an approximately piecewise linear approximation to give predictions that are consistent with what we think the mean of the noisy pileup spectrum is. So in that sense, I don't think that we've run into any surprises.
Does anybody approach this problem using Gaussian processes? That's a current fad. It strikes me that might be an alternative to your simulations.
Yeah, that's a good point. I don't know, but I'm probably missing some people's work.
How would you use this question? Well, I guess there's a question for Jeff. What were you thinking of when Jeff is, how would you apply GP to this problem across stage?
Oh, well, that's yeah, that's a good. I guess the way you would do it would be to actually have an explicit model for pileup. And so that would be a major difference from what you're doing, because as we discussed, you're not modeling the detector, the action of the detector. But I don't know. I'm sure there in the room or on Zoom there are people who know much more about Gaussian processes than I do. Sometimes
if you're not afraid of high dimension spaces, you have 600 channels or something, so you can calculate the 600 channels of input and 600 channels of output. That's a point in a 1200 dimensional space, and you do that 17,000 times, and now you infer the Gaussian in that 1200 dimensional space, and then it's a trivial matter to predict 600 of its dimensions conditional on 600 other dimensions. The question is whether that thing at all looks like a Gaussian in the 1200 dimensional space, because if it doesn't, you'll do something miserably wrong.
I think that's exactly.
Yeah, go ahead.
I think that's exactly the point. I don't think the dimensionality is, I mean, these people claim that they're dealing with infinite dimensional representation. So high dimensionality is not a bother. But I think you're absolutely right. It only works if everything in the process from the beginning to end has a Gaussian distribution. That's the only way that the method works. And I don't know if that's even a crude approximation here or not.
Well, it would be an easy thing to try, actually. So thanks for the suggestion. I mean, I kind of doubt it'll work, right? But it's actually an easy thing to try.
Yeah.
It's just a few lines of code. Well, I mean, 1,000 lines of bookkeeping and then a few lines to do the actual matrix operation is what I mean.
Yeah.
Sure. For some people, it's code. That's the case.
Herman?
Yeah, I got two comments about one is it seems like you could also try this on dispersed spectra that are piled up because that actually occurs in some of the brighter sources and is a bit of a bugaboo for certain folks looking at the modeling the continuum precisely. The interesting thing there is that you don't have the entire space of energies piling up on each other. It's just really one or two energies that are piling up with, and so you can actually it's probably a more tractable problem.
Why do only one or two energies pile up on each other?
It's dispersed.
It's dispersed, so you expect first order and second order to be on the same location, and then and so all of the energies that'll pile up are going to be multiples of the one energy. Although,
I think I understand. Okay.
yeah, you could also look a little more at how the grade migration changes. The other thing I wanted to suggest is kind of akin to what Jeff was mentioning earlier, which is that one way to test this kind of thing is to actually look at a variable target where you know the spectrum doesn't change as it varies, and see if you can get the light curve properly.
The spectrum doesn't change.
Yeah, yeah, for a case where the spectrum doesn't change as it varies in, say, some kind of mild manner.
But how do you know the spectrum doesn't change?
Well, Jeff says that he does.
No,
Well,
Well, that was a lot of experiments.
yeah,
no, you can assume it, but here, can't you just generate synthetic spectra that by definition or don't change? You can do simulations, ab initio simulations to do what Herman is getting at, I think. Or, sorry, I'm
Not any better than this training data, because you still rely on the marks to be correct when you generate them.
Yeah,
Yeah, it sounded like for what Herman was saying about source. About picking a particular source, that would be a check on whether the trained neural net is able to map from unpilot to pilot spectrum. Is that correct? Is that what you were thinking?
I'm not sure.
I think that what's promising is similar to what you said, which when you have a pilot up imaging spectrum, you almost always have the readout streak, and the readout streak will typically not be pilot up.
I think
So
a
you
better
compare the
case,
spectrum,
yeah, a better case
the
might be
readout streak with the pilot up.
in a ring around a source that's piled up, you have the same incident flux, and you can actually use them as separate detectors essentially to analyze the pileup.
Right, so I guess that could be a supplement to what I was talking about with the grading data, where instead of using the gradings, you could say that assuming that the source has the same spectrum.
Well, it's a
in-
point source. You use a point
Well,
source. And you
yeah.
assume that PSF is constant, which it's not, but it's probably really, PSF changes slightly with energy, but only slightly if you don't.
I was thinking of something a little bit different in that at a given radial angle from the point source, the spectrum should be approximately the same all azimuthally. And therefore you can treat them all as independent samples of the same spectrum with the same pileup. And if you move your way in and out of the PSF, you will have different levels of pileup for approximately the same spectrum.
Right, unless you move too far, because the PSF is energy dependent.
Yeah. But it goes in a way that's straightforward to model. Because that's just the PSF at different energy ranges.
Okay, yeah, thank you for the suggestion.
all right, we have hit 1:30 PM here, so yeah, timing. Thank you again, Justina.
Thank you.
And we have a remote talk, at least from our perspective next week. Robert Zimmerman will be joining us from Imperial, talking about what is it? Hidden marker models. So
Should be kind of online, but we're not being.
we're not in. All right, so see you all next week.
All right, thank you, everyone.
Thanks. Interesting talk. I enjoyed it. So.
Thank you.